Okay. Did this previously and apparently I didn't stop the video or Zoom. Well, whatever. Okay, so I've got this car here and a piece of paper, and watch what happens now. I move paper at a constant speed after I accelerate a little bit to get it motion, and there we have. Okay, so I asked everybody then to sketch a three-body diagram. And most of the diagrams I saw look something like this. Okay. Now the question is that an equilibrium situation? Well, no. However, okay, this system is not an equilibrium as drawn. However, net equals MA, and if your velocity is constant, your acceleration is zero. So we have a contradiction. Okay. Definition of equilibrium, since A equals zero, implies that your net force is zero. Clearly here, the net force isn't zero. You add up all those forces and you get that. Okay. This means that there was zero net force. This means if you don't have a force going this way, you can't have a force going that way. So that nobody can think of a force goes this way when I'm pulling the thing. Okay, and there's nothing even intuitively that gives you the idea that there's a force in this direction. So in this case, you don't have that force. Okay. And that's it. You just constant, this is what you got, and you don't got this. Okay. Now I'm going to do this again. Ready? Oops. Things up against the board. Actually, let's do this. Okay. What happened there? Well, let's make a mark. On paper. I'm going to make a mark on the paper at the front of the card. Okay. Let's see what happens. Now the car actually ended up in a minimum position about here, and then it went forward a little bit at the end. So what I've got is the disaster. Oh, for that. Yeah. Okay. I've got 3 marks on the paper here. Car started here and it ended here. Okay. Then I actually think the paper was like this. It started here, ended here, then moved forward to here. So what's going on there? Paper didn't move at a constant velocity. Paper was accelerating, which means that the car is probably accelerating. Okay. If it hadn't been, paper probably would have left it behind. Now we could analyze the motion and see that. But in that case, the free body diagram did look the way you wanted to draw it in the first place. You had this situation with the normal and gravitational forces in equilibrium. You also had a net force here. And cause the car to accelerate. What's the source of this force? Yeah. The frictional force we're going to say is the same at any velocity. As long as the car moves with respect to the paper. Which it did. You can tell by the marks, the car did move with respect to the paper. Okay. So do it again. We'll start the car in the same place as we did before. Okay. Ready? Car was moving with respect to the paper at pretty much every instant, and it pretty much didn't go anywhere at all. Okay. But it went a little ways. Okay. The car had a certain acceleration in the frame of the blackboard. Okay. In one case, I moved things slowly, and the car moved from here to here. Less than the paper did. The paper moved that much further than the car. Car had a certain acceleration. Its velocity wasn't constant. If the velocity would have been constant, it would have gone from here to here, but it only went from here to here. Then when I pulled the paper out quickly, we didn't really detect any motion. It might have moved a little bit. What's the difference? Well, the difference is that in this case, the car had a while to accelerate. Had a few seconds to accelerate, didn't it? How much time do you think the car had to accelerate here? It wasn't zero. It took a little while for that paper to pull out, right? If I pulled it at about this speed, okay, what's that, 90, 100 miles an hour, something like that. Okay, well, it was a few meters per second. Okay, that started at zero and accelerated, but it accelerated pretty rapidly. So that there was very little time for the frictional force between the paper and the wheels to accelerate the car, so it didn't pick up any significant speed. Now I could accelerate it faster than in the first case, but a little slower than I just did. See, it moved a little bit, didn't it? You see it? You can always look at the video, but it moved maybe a centimeter or two. Probably closer to 1 centimeter, but there was a margin for that. Okay. The paper was accelerating faster. The car didn't have enough time to speed up very much. But the free body diagram is the same in every one of those cases. Okay. So in the case where the car is not accelerating with respect to the paper, and the paper is moving at constant velocity, the car is moving at constant velocity. Okay. Now there's another case where I can accelerate the paper, but accelerate it pretty slowly, and the car doesn't move with respect to the paper. That would be this case again. I'll demonstrate that, I think. Okay. In every other case, the car moved with respect to the paper. This was it. And your net force was just a frictional force. The faster I accelerated the paper, the greater the acceleration of the paper, the less time the force had to act, so the less displacement there was of the car relative to the root. Okay. So just, the third case, it goes back to the first. Okay. Level, here we go. Definitely speeding up. You see me speeding up? Getting faster and faster, but the car didn't move. The frictional resistance was sufficient to keep it on the paper, basically. Free body diagram is the second. Okay, that's important. It would be important in the assignments you'll have in chapter 5. There's several examples of that. There's an example, I know it's in the problem set in the text, and I think there's one much like it in the online assignment. You got a box in the bed of a truck. Okay. I got a box in the bed of my truck and the back is open. But let's just say I got lumber in the back of my truck. I screwed that up the first time I ever tried it. I forgot it was there and just accelerated too fast, and all the lumber dumped out in the road. Yeah, it wasn't that big a deal to get it back in, but it's kind of embarrassing. Okay. Yeah, if you accelerate the truck slowly, there's enough frictional force between the lumber and the bed of the truck that it doesn't slide with respect to the truck. Okay, the frictional force is sufficient to keep it accelerating at the same rate the truck is accelerating. If I accelerate the truck too fast, frictional force isn't enough, okay, so that the lumber can't keep up with the acceleration of the truck. It accelerates, not fast enough to keep it in the bed of the truck. That makes sense? Think of the free body diagram. Now there's another technicality here. There is a difference between the situation where the free body diagram looks like this because V was constant and what it looks like if V is not constant if the acceleration is low enough, keep the car moving forward, okay? I'm just going to say this, I'm not going to draw it out. It's in the interest of time. This frictional force, if the car is stationary with respect to the paper, it's static friction. Static friction is less than kinetic friction. As soon as you break static friction, you have kinetic friction, the friction drops considerably. And we can demonstrate that. Might not be able to demonstrate it up here because I have to be pretty low, but here. Okay. You're going to increase the force gradually. There's a little force, I can feel it. I keep pushing a little harder, a little harder, a little harder. Oh, there it goes, right? Now it moved. Okay. As soon as I got up to the point where the frictional force, or where the force of my fingers could equal the frictional force, as soon as I went past that point, this thing all of a sudden accelerated. Okay. Now it didn't move very fast. If I had a big box on the floor and was pushing a refrigerator, say, that didn't have wheels, they didn't used to have wheels, and they used to be a lot heavier, it used to be a lot of fun. Okay. Well, when I was young, it was okay. But I wouldn't want to try it now. And not with refrigerators and ovens. Okay, so anyhow, you're pushing something heavy across the floor. And it takes a lot of force. So you push, and all of a sudden it breaks free, it starts moving, starts accelerating pretty quickly. You had that experience? You understand what I mean? It's because you go from static friction to kinetic friction. So let's say it takes 50 pounds of force to move that box. You exert 50.01 pounds of force and it starts moving. All of a sudden, the friction drops to where maybe exerts only 30 pounds against your push. So you got a net force of 20 pounds on that box and you accelerate. Now, if you want to push it at constant velocity, you just drop the force you're using and you just keep it moving. Okay, keep moving at constant velocity. It means you drop your force to 30 pounds. You just do that instinctively. You can't keep accelerating with that 20 pounds forever because you keep speeding up. Pretty soon you'll be going faster than you can go. Okay. Well, that's a little bit about how friction works. You can relate that to what you read in your text and to what you see in any support that the online materials give you. And of course, probably do some experiments where we measure that stuff. One experiment that we'll probably do, you can just imagine that there's a string attached to this box that goes over this low friction pulley. Okay, call that a smart pulley. That's the manufacturers will call it for here. Built those things, and they're very good pulleys. It's still moving just under its own position. Okay, it's got pretty low angular acceleration. So we hang weights over the end. Then we gradually add weight. Maybe we just hang a bunch of 0.4 of a gram paper clips until this thing starts moving. As soon as it starts moving, it doesn't just move at a constant velocity, it just starts speeding up. And you can observe that. You can time it from one point to another. And actually, it's a little tricky. Not that tricky. Okay. I mean, we talked about the analysis. Anyhow, there we have. Okay. So make sure you understand that much about friction, because you're going to need that insight to understand the problems. Okay, I've got a set of weights. There's a 100 gram weight and a 50 gram weight and a 100 gram weight in a 200 gram weight. I think I said 200, 250, 100, 200, and then the hanger itself is 50 grams. And there's a nickel on top. And we're going to focus on that nickel. Now, right now, what's the free body diagram for that nickel look like? Well, we're not accelerating. Okay, I mean, it's wobbling a little bit, but let's ignore that. Okay, as far as upward motion, it's not really going anywhere. So that the normal force has to be equal and opposite to the gravitational force, right? Now, if I do this, okay, between the low point and the high point was the acceleration constant. We ought to be able to answer that. Of course, you're not able to answer because this thing's on. You ought to be able to answer that in terms of what we saw with that ramp last time. Okay, it went from here to there. It was stationary when it was released. It was stationary when it stopped. Well, my hand and the whole system was stationary here, raised it up, and it was stationary here. That held it there for a minute, then I brought it back down. Clearly, there was an acceleration because the initial and final velocity for each of those phases were both zero. There was no change in velocity. The average velocity, or the average acceleration, which is change in velocity by the time interval, was zero because of no change in velocity. But it went somewhere. If the acceleration stayed zero, it wouldn't have gone anywhere. You really want to understand that argument. We talked about it last time. So it's the same argument here. So there was an acceleration in between. And there was therefore, if you just use little calculus with Rolle's theorem and intermediate Rolle's theorem and stuff like that, probably didn't get covered as much as it might have. No fault of the instructor. And maybe it was, I don't know. I really probably ought to talk to him and ask. Just to see, what I can expect. Anyhow, there are theorems that tell you that if you go from 0 to 0, I don't want to rephrase it. You have velocity 0 here, you have velocity 0 here. You don't have velocity 0 all the way. So there was some maximum velocity, and then it was continuous. There's some maximum rate of change of the velocity. Okay. And it's intuitively obvious that there was a point where the thing was accelerating more than it was at any other point. Okay, so maybe from here to this point, it was accelerating in the positive direction. And then from here to this point, it was accelerating in the negative direction because it was slowing down. Okay. Acceleration went from this direction to this direction. And the average of this and this somehow turned out to be 0. Okay. That's just a simple conceptual idea. You don't even really need the formal arguments of calculus, although if you really want to be sure the argument is correct, you use it. Okay. At the time when the acceleration was its maximum in the upward direction, what did the free body diagram for that nickel look like? Can you sketch that for me? Okay, well, we can frame the thing with a picture just to indicate a few things. We start here at v equals 0, we end here at v equals 0. So our average velocity is clearly positive. If the positive direction is up, I've got a plus with an arrow here indicating that's the positive direction, okay? So this is a positive direction. Your average velocity was positive, okay? But your average acceleration was 0. Because, of course, there's no change in velocity between here and here. Your average acceleration between here and here is change in velocity divided by change in time at 0. Well, we conclude that the acceleration is non-uniform between here and here. Sometimes it was positive, and sometimes it was negative. Okay, and we can say that more intuitively. Let's say we had an increasing acceleration over this interval, right? And a decreasing acceleration on this end. Okay. You don't even have to posit that the acceleration was increasing. It was, but I'm going a little too far by saying that. We will study simple harmonic motion. We'll begin studying that before we actually formally get to it. And in simple harmonic motion, everything I said there is correct, but all we really can say right now is that this is positive acceleration, negative acceleration. I shouldn't use the increasing and decreasing, even though it's so. Okay. The maximum acceleration occurs between positive and negative acceleration. Well, and that's not even necessarily so. Maximum velocity occurs between the positive and negative acceleration. Maximum acceleration occurs somewhere between here and here. And I'll put a question mark next to those little arrows to indicate we're not sure where it occurs, but it occurs someplace. Okay. In simple harmonic motion, it would occur immediately. It would occur here. And it would be positive but decreasing until it became negative. And continue increasing. Okay. Now the question was free body diagram. What's a free body diagram look like? So let's see what you did. Okay. There are only two forces acting on that nickel. There's a normal force between it and the grass weight it's resting on. So you got a normal force. And you've got the gravitational force, which is down. They aren't equal and opposite, because if they were, you'd have zero acceleration. So just to indicate that, I wasn't accelerating that rapidly. It would actually be pretty close to the length of the normal force, but we want to emphasize the fact that it's less, okay? It's harder to write is correct. F net is upward. So that your acceleration is in what we chose to be the positive direction. Okay, what does a free body diagram look like when you have the minimum acceleration, that is the greatest negative acceleration? What's a free body diagram? Negative acceleration rates. And I didn't take time to look but I think you probably have it. You could have a normal force. And you'd have a gravitational force. Actually, this picture doesn't relate well to this picture. So I'm going to redraw it. I mean, there's nothing wrong with this picture, but if your scales are the same, then the gravitational force is not going to change its length. So let's just make the thing, scale it equally. Okay, so you got the gravitational force, we'll say it's here. Then you got the normal force. Up here, and it's less than the gravitational force. So that your net force up here is upward, so your acceleration is going to be upward. And down here, F net is downward. One's going to speed you up, there is going to slow you down, assuming you're moving upward. Now, if you're moving downward, if you go from here to here, how does that change picture? How does that exchange? How does that change your free body diagram? Something I want you to think about. I'm not going to take the time to do that because there are other things we want to talk about, okay? I'll also mention that the most common type of motion you have in the whole universe is simple harmonic motion. And this is just a preview, but it's like this. It's an oscillatory motion. This is an approximate simple harmonic motion. It's like the mass at the end of a spring, where the force pulling it toward the equilibrium position gets greater in magnitude the further you go from equilibrium. You stretch that rubber band out, as the thing descends, you get more force in this direction, right? Then you come back to equilibrium, that's where it was hanging without any motion, okay? That'd be your equilibrium point. And then you go above equilibrium, and now you get less force from the rubber band, meaning the gravitational force takes over, and you get a maximum force when you're up here. A force of maximum magnitude. Net force of maximum magnitude pulls you down, and that force is linear. So it has a form F net equals Ky, if y is your position, or Kx if you're moving in this direction, okay? If F net equals Ky, then mass times acceleration equals K, well, let's say Kx. Let's say net force is Kx. Then your acceleration is Kx, right? Well, Kx over m, over the mass, okay? Your acceleration is second derivative of your position, so you have the second derivative of x being a negative multiple of x. And that's a simple, very simple second degree differential equation. It's like x double prime plus kx equals 0. Okay. Use your multiple of e to the I theta or whichever, or e to the RT, and solve it. So a lot of what we said here applies to that in a very specific way. Your solution is just a sine function. Second derivative of a sine function is a negative multiple of the sine function. The first derivative is cosine, derivative of cosine is negative sine. Okay, you apply the chain rule and you get all the k over m's and stuff like that. So you've seen that. So when we do that, everybody in the class has had differential equations, so we kind of make short work of the mathematics. It's a completely different set of equations of motion. So get used to the idea that acceleration is not always uniform. And the reason I say it now is I want to caution you, at the end of the semester, I don't want to see anybody using uniform acceleration to model an oscillatory motion, because the oscillatory motion, zero here, velocity zero here, velocity zero here. So there's zero average acceleration. Equations of motion, uniformly accelerated motion, are no help at all. Just kind of store that away. That's the first time I've said that. I'll be saying it many more times, because we get to the final exam and people want to pull out the equations of uniformly accelerated motion, simple harmonic motion where acceleration is demonstrably, very clearly not uniform. Make sure you only apply these equations when the acceleration is uniform. I say that also in advance of the test, because you have had problems where acceleration is not uniform and you got to integrate or take a derivative, right? It's usually a simple polynomial in this case, and the derivatives and integrals are really simple, but you got to be able to do that. Okay. I'm not going to have you do it. Well, I could give you the equation of motion and ask you to differentiate it. It's just a sine function. Very simple. I don't have anything like that in the problem set, but if I put it in there, it would be one of the easiest problems on the test. Okay. Because all you got to do is know that the velocity is a derivative of the position, acceleration is a derivative of the velocity, and you go in the opposite direction, you have integrals. Okay. Everybody is very well versed on that. So you hope that I'll put an equation like that on the exam. And I might well. Okay. Haven't really thought of it yet. But I do have things with other non-uniform accelerations, you know, like an x squared or a square root of x or square root of t or whatever. Okay. Okay, now, you know, what I just did was acceleration through 20 centimeters and something between 1 and 2 seconds. And I asked you to calculate the average acceleration. It's a very simple reasoning process. If you start from rest, you don't need to confuse yourself with the equations of motion, although it shouldn't be very confusing. You can shortcut the whole thing. Okay. In my example, let's say we go, okay, so we've got like this mass here with a 5 gram mass sitting on top. That's the nipple. Our delta y, if I accelerated it through 50 centimeters uniformly in 4 seconds, what would my acceleration be? I plug into the equation of motion to get that pretty easily, but I can figure it out very directly. I divide the 50 centimeters by the 4 seconds and I get 12.5 centimeters per second. That's my average velocity, my delta y over delta t. That's my Vy average. My initial velocity was 0 from rest to Vf, right? So my average velocity has to be the average of 0 and my final velocity. So the question becomes, what would I average with 0 in order to get 12.5 centimeters per second? Well, it'd have to be 25 centimeters per second. Okay, so my final velocity has to be 25 centimeters per second. You should try to understand that and understand why it's necessary. Not totally necessary, but to use a shortcut. We generally use that when we start from rest, because then we know that the final velocity has to be double the average velocity. And we can then just divide that by the time and we get the acceleration. Okay. So my question is, what's the force on that nickel? What's the free body diagram look like for that nickel? Now you've got an acceleration that you found one way or the other. And even if your acceleration is wrong, you can go ahead and use it. So here I've got a free body diagram. And the nickel is represented just as a dot with a mass of 5 grams. What's the gravitational force? Well, it's 5 grams times the acceleration of gravity. What's the normal force? Well, net force is your normal force plus your gravitational force, which in this case equals your normal force minus mg, and I'll say times the j vector since we're in the vertical direction. And I've got arrows over these, I better make this a vector. Okay. It's safest if you do that. Okay. So we know that there are only 2 forces. F net is the sum of those 2 forces. One of those forces in the negative j direction, the other is going to be in the positive j direction. But we don't know that yet. I mean, we kind of do know that, it's pretty obvious. But what's F net? I haven't left myself a lot of room here. F net's your mass times your acceleration. Your acceleration is 6.25 centimeters per second squared times the mass. So we have 2 things that we know. We know that F net is mass times acceleration. We know that F net is the normal force minus the gravitational force. Well, I'm out of room, so let's just write all that up here, where we can label it a little better. So there we have it. And we also have net force. And net force is normal force minus mgj, and F net equals mass times acceleration. You're given the mass, you're given the acceleration. Five grams times 6.25 centimeters per second squared times the j vector, because you know it's accelerating upwards. That's the way we did it. But we can then write this equation, rewrite it, you can solve it for F naught. Normal force is net force plus mg times j equals, well, 5 times 6.25 is 30.125. $31.25. So I'm going to say it's approximately 31 what? What are the units of this net force as I've expressed it? Okay, I got two answers. First answer I got immediately, it's newtons. Well, no. Newtons is what you get when you multiply mass in kilograms by acceleration in meters per second squared. A newton is a kilogram meter per second squared. It's not a gram centimeter per second squared. So it's 31, just, the units are what you get when you multiply these units. It's 31 gram centimeters per second squared. Well, a gram is 1/1000th of a newton. Okay. And a centimeter is 1/100th of a meter. So you got 1/1000th of a kilogram times 1/100th of a meter gives you 1/100,000th of a newton. That's just what that unit is. It's 100,000th of a newton. Okay. So you're going to divide 31 by 100,000. You get this. Okay. Now let's just note that gram centimeter per second squared is 0.001 kilograms times 0.01 meter per second squared, which is this, which is 10 to the negative fifth newtons. You don't have to go through a bunch of rigmarole with multiply by grams over or kilograms over grams and multiply by meters over centimeters. Okay. Although that's essentially what we've done. And you can write it out that way. But it's very simple. If you've got these units and you know how many of these there are in these, how many of these it takes to make one of these, how many of these there are in one of these, or how many of these it takes to make one of these. Okay, as long as you do it carefully, it's a little more direct to do it this way. You should be able to do it the other way too, because sometimes you really need to keep track of things. Okay, so this is at mg. Well, I'm going to use 10 meters per second squared. We're off by 2%. It's not going to bother that nickel very much. Okay. And you can always take 2% less. So approximately. And since I made that approximation, I might as well just make this 0.0003 newtons plus 0.05 newtons. Plus 0.0503 newtons approximately. Now the whole process is, I don't use my intuition, although intuition would work pretty well here. I write out Newton's second law. F net equals MA. I write out F net equals F norm minus MGJ, because I know what that force is. Okay. And then I set this equal to this. Or I just solve this for F norm. It's really the better way. You just write out what your F net force is. You just write all your forces. And then if there's one you're trying to find and you know all the others, you solve for it. So we solve for F norm here. Get this we get this, and it makes sense now. We've got 0.0503 newtons up and 0.05 newtons down, giving us 0.0003 newtons up. Okay, which is what it takes to accelerate that nickel at 6.25 centimeters per second squared. That makes sense? Yeah, kind of focus on this equation and solving it for F norm and then filling in everything else. It's really what we're doing.